Just put a wrench through the hub to be able to loosen this and break the Loctite loose. Okay, there we're free. And now let's push out the bearing assembly. There's the bolt. And just need a pin to push out the bearings. Okay, there's the bearing stack. And if we look at the bearing stack here, we'll see there's just two bearings side by side, and there is no spacer or anything in between them. Okay, here's the stock setup. You can see the amount of play that we have here in the hub. We've got quite a bit of rattle there. If I hold it a little closer, significant rattle. I think what's happening here is when this blade cocks, since we have the bushings, we're very close in the pitch links. I think we're getting binding in those because of the amount of lean of the hub. As soon as that goes that far of an angle, we're binding up the pitch link. So we're going to make a spacer to go between these bearings and a crushable inner race spacer so that we can actually tune these to get them preloaded very gently like a Kasama style, except we're not having a thrust and a ball, but we're having two balls, but they can still be preloaded in the same way to get rid of slop. So we're going to do that. Here we're showing the approximate center of pressure of the blade where the pencil mark is, and the bearing set where it is actually located in the hub, and what the distance is, what the moment arm is on that bearing set to the center. And you see here we have 28 millimeters of moment arm. And what I'm showing here, I'll draw a little diagram on a post-it to show you the difference in forces on the bearings just by spacing the bearings a little bit. So right now we have a 28 millimeter moment arm, and we'll draw a little diagram and show what we're trying to accomplish with the spacer, besides the preload effect. Okay, here we have the physics of what's going on in this assembly as far as bearing spacing. All we're trying to do here is understand what the effects of changing the spacing of these bearings does to the loads that they see. This is the center of the pressure of the blade. It's not exact. If we actually calculated where it was and took everything into account, it might not be the exact spot, but we're using this strictly to get an idea. So approximately this is the center of pressure. 10 ounces of blade force, also not probably what it is. It's just an example to be able to use some numbers in the math. When we push on the blade out here, which is attached to the outer races of the bearings, as we push here, this outer race moves down in this direction. This outer race wants to move in this direction. So that's what we're showing here with these arrows, the forces in their two opposite directions as we push out here on the blade. When we take this 28 ounces and 10, that's a moment arm, 28 times 10, we divide it by this and we get what the actual force is. So for that 10 ounces of force, we have 233.3 ounces of force seen on the bearings, and for all intents and purposes it's equal. It's this direction on this bearing, this direction on this bearing. So a 23 times magnifier because these are spaced so closely. If we add the 1.4 millimeter spacer, which is what I'm intending to do, that's only limited by the fact of the head of the screw starting to touch the back of the blade in the grip, which obviously we can't have it rubbing because it would tend to keep the blade from spinning freely. So 1.4 is as big as we can go, and when we do that, we add the 1.2 spacing. We put the spacer in between. The spacing is going to grow by the 1.4. We do the same math, 107.7 ounces. So just by putting that spacer of just 1.4 millimeter, which is a little over double, we have a little over double reduced the forces seen by those bearings. So that's what
the whole purpose of putting this spacer set in is to drop this down. Second purpose is for getting rid of the play, and we're going to show what the contact angles in the bearings do when we do that. Okay, this is a diagram showing what's going on with bearing preload. This is a sketch of what's going on in the blade hub. We have the blade grip here, we have the hub here, we have our two bearings, and now we're going to be adding spacers. This spacer being rigid, this spacer being crushable to be able to get to a preload condition. As you can see here, in a ball bearing, the actual race radius is not equal to the radius of the ball. It has to be that way in order to allow for minor misalignments and to have a reasonably small contact patch between the ball and the race. So when you have a ball bearing, which everybody's experienced, the inner race can move back and forth, has some slop in it, which is designed in. It's the amount of radial play that's designed into the bearing to enable it to withstand some misalignment. When we put a spacer in or leave this out where we can pull the inner races towards each other, we see that these balls move to where this ball starts to ride over on this side at the one side, and then in the outer race it rides opposite, and it develops what's called the contact angle. It's strictly what happens with the radius combination of these two, where they are, their diameter, and the size of the ball, and when they make the bearing they calculate where that's going to be to come up with a particular clearance or contact angle. What this does is this makes us get to the point where we can preload this. This is no different than our old bicycle front wheels cup and cone bearings, where we used to adjust the play in the bearings back when they had those, and to be able to adjust to where we had a no play condition. So what we're going to do here is we're going to have an outer race spacer 1.4, an inner race spacer that starts out at 1.4 but is a soft aluminum so that it can be crushed by the force of the screw and just get shorter as needed, but still give some resistance to the screw so that as the Loctite cures, we have a good stable setup. When we do this, we need to be certain that we just get to the preload point. You can put too much force on and crunch the balls and put dents in the races, and then we've got your typical notchy bearing situation. This obviously can be accomplished in a different direction, where you push the outer races or the inner races out and pull the outer races together, but then that changes the contact angle to a diverging. You see here, this is called converging contact angles, where they converge on the outside, and the other would be diverging, where it would be other. This is the strongest for resisting moment loads, which is what we have here. We have the blade grip wanting to push sideways, and this is what you want. So what we're doing here is the ideal preload situation for.
This is the spacers that we've made and the sequence that they would go into the blade grip. The outer spacer is brass, the inner spacer is a soft aluminum, which will allow the bolt to basically crush it. The inner race surface will bear into the aluminum and just crunch. Basically, it's the real soft, like 1100 aluminum, so it's it should easily be crushed to get the preload that we want. So we're going to lube these bearings a little bit, and I would suggest, see how the shield on this bearing, the back of the shield is towards us. I would suggest putting that towards the outside, just like we do with the thrust bearings, to cup the grease and hold some of the grease into the bearings. So I'm going to lube these, and then I'll show the assembly sequence.